Hi, my name is Nathan Zeringue, and I am presenting my major assignment B for heat and mass transfer for Dr. Jimmy Lawrence, and I am determining the necessary heat transfer rate of a CPU fan. Around the world, about 50% of all households have computers, and in those computers there are a lot of essential parts like the graphics card, the motherboard, but most importantly the processor. And these components require cooling, and a lack of cooling can be detrimental to the lifespan of the computer. So the central processing unit, or the CPU, is basically the brains behind the computer. So the CPU runs all the programs and executes functions in these programs, and this generates a lot of heat. So a CPU fan is required in order to cool the fluid surrounding the CPU. Most commonly air, but sometimes it is water in a closed system, or mineral oil surrounding the components. So what we'd like to determine is the heat transfer rate of the CPU to the surrounding air. To calculate that, we need to measure a few things. So I measured the CPU fan speed at different temperatures of the CPU, as well as the temperature of the surrounding air, the dimensions of the fan, and something known as the tip speed ratio. With these, you can calculate the wind speed, the Reynolds number, Prandtl number, Nusselt number, the thermal conductivity, heat transfer coefficient, and viscosity. And all of these can be used to calculate the heat transfer rate of CPU to the surrounding air, which is Q. So from this measured data, we have the CPU fan speed in RPMs and the fan diameter. And these two things can be used to calculate the blade tip speed, or BTS. That, along with the tip speed ratio, can be used to calculate the velocity of the air passing over the CPU. And this is assumed to be parallel over the CPU. With this wind speed, we can calculate the Reynolds number, and then with the Reynolds number and the Prandtl number, we can calculate H, which is the heat transfer coefficient. And that we can use that second to last equation using Nusselt number if Reynolds number is laminar. So using this equation, we can calculate the heat transfer coefficient, which can be used to calculate the heat transfer rate, Q. So in actually measuring this data, I set a low CPU usage and a high CPU usage. And this caused the CPU temperature to increase, which increased the CPU fan speed. And so what we got is two CPU fan speeds at 2,410 and 2,950 revolutions per minute. And this gave us two CPU temperatures of 35 degrees C and 75 degrees C. And this data was measured over 20 minutes to ensure that the CPU reached steady state. I also measured the temperature of the surrounding air and the diameter of the fan. And you can see on the right here the software interface that I used in order to calculate the temperature and fan speed. So what you're looking at here is the data that I actually collected. So you could see going from left to right, I calculated the CPU fan speed, the temperature of the CPU, the surrounding air temperature, as well as the diameter of the fan. And from that, I can calculate the blade tip speed. And then using the tip speed ratio, we can calculate the wind speed. And in that calculation, I used a tip speed ratio of 2. So where does this tip speed ratio number actually come from? So from literature data, we know an upper and lower limit of the tip speed ratio at different numbers of blades for the fan. And so on the right, you can see a graph that shows a model, and you can see the orange line, that's the upper limit of the range of the tip speed ratio, and the blue line is the lower limit of the range. And so from this data, we can create a model, which you could see the R squared value lets us know that this is a very accurate fit. So with this model, we can extrapolate a tip speed ratio number for a CPU fan that has 7 blades. And with this extrapolation, we find that the tip speed ratio of a CPU fan with 7 blades is about 2. So with this data on the left, which is the density, dynamic viscosity, specific heat, and thermal conductivity of air, we can calculate the Prandtl number, the kinematic viscosity, the Reynolds number, and the heat transfer coefficient. Now, in these calculations, you can see that we get a Reynolds number of between 3,800 and 4,800. So this flow is laminar. And with this calculations, we could see that we get a heat transfer coefficient of 23.98 and 26.54 at the lower and upper CPU fan speeds, respectively. So with this data that we've calculated, calculating for the heat transfer coefficient H at these two Reynolds numbers, and we know the area of the CPU, as well as the temperature of the CPU at these two CPU fan speeds, then we could calculate the heat transfer rate Q at this upper and lower CPU fan speed, which we get 0.35 watts of heat transfer at the lower CPU fan speed and 1.93 watts of heat transferred at the upper CPU fan speed. So in conclusion, when we increase the CPU usage from around 0% to around 100%, we see an increase in the CPU temperature from 35 degrees C to 75 degrees C. In order to keep this heating under control, we need to increase the fan speed from 2,410 to 2,950 revolutions per minute. From that, we can calculate the speed of air going across the CPU of about 1.575 and 1.93 meters per second, respectively, for those two CPU fan speeds. And with this, we can find that the heat transfer rate of the CPU going to the air will increase from 0.35 to about 1.93 watts as we increase our CPU usage from about 0% to about 100%.